All right. Well, welcome and good morning into afternoon. My name's Nick Crozier, been with Greenheck for 5 years, looking at the makeup air presale side, also handling energy recovery. So today we're going to talk about industrial space heating. So getting right into it. Heating large open spaces. So you're looking at warehouses, distribution centers, and manufacturing facilities. What are the challenges with that? Obviously, wide open spaces. Sometimes you don't necessarily need a lot of changeover with air. You don't have maybe a requirement. Sometimes you'll see a CFM requirement. A lot of the times people say, hey, don't let my building freeze, or I need 50 degrees. That's it. Make it happen. Well, what are the challenges with that? Obviously, numerous dock doors, sometimes entire face walls of dock doors, tall ceilings, and heat distribution. Stratification, number one issue you'll most likely see in warehouses, especially with tall ceilings. It's the development of different layers of temperature inside that space. Hot air rises towards the ceiling, cold air falls towards the floor, increased overall heating load. Why is that increased? It's due to that hot air rising, creating that hot air bubble up in the ceiling where you continually provide more and more heat. It builds up on top, but it's not necessarily heating the entire space, and as seen below there. So, space heating design, what are your considerations? Well, first, overall skin load. So what is that? It's the conduction losses. So you're looking at overall, you need to go over these four details when you're considering and even trying to apply heating to that warehouse. So first, the skin load, like I said, conduction losses. Then usable heat. It's the energy available to heat the space inside the building. So what is that? Usable heat is basically, say it takes 1,000 MBH to heat a building at 70 degrees. To get to 71 degrees, if you have 1,000 MBH, you can't. So any usable heat is the heat after you've met the intent of that space. So say you have 1,200 MBH and it's 1,000 to get 70 degrees maintained. Well, you have 200 MBH of usable heat after the fact. That's how that is used. Infiltration, cold air. So coming in through doors, service doors, dock doors, poorly insulated areas, non-sealed areas, general infiltration, and heat distribution both across the space and floor to the ceiling, especially stratification. So distributing that heat evenly, not having that bubble again up in the ceiling. Infiltration, air leaking into the building through the doors, windows, cracks, dampers, etc. Effects of infiltration, increased stratification, reduces space comfort, and increased heating loads. Again, that diagram showing the open dock door, cold air infiltration coming into the space, then mixing where your warm air is forced to the ceiling. So say if you are heating, maybe an air turnover unit or something like that, that's heating more towards the ceiling, not directly blasting down, it will most likely mix and have that hot air pocket above with cold air infiltration below through the doors. Next, combating infiltration by looking at building pressurization. So this is the key detail in our market, especially with our direct gas units for space heating. The big ticket is combating infiltration through pressurization. So what are you doing? You're bringing in that CFM, you're pressurizing the space, you are pushing against that infiltration, that cold air. You have multiple dock doors open. If you're bringing in that makeup air, you are creating that entire bubble of the space to push that out. It's that heat air curtain kind of dropping down and preventing that cold air from coming through those either open doors or other infiltrated areas. You can see that infiltration rate, simulated wind speed. So on the bottom of the graph, it talks about the speed of the wind going up. On the side, it talks about your CFM value, and the two different numbers there is one with a positive 0.12 inches water column, and the red would be a negative. So you can see how it actually less CFM is needed there when you have that positive pressure and you're keeping that out. Calculating infiltration. So infiltration is difficult to calculate. Some methods include air changes, hour method, rule of thumb, the crack method, CFM, linear. Considerations. The big thing is building construction, building size, number of doors, overhead drive indoors. So the big thing when you're looking at that building construction is insulation. That's the key detail. Just moving an R value of 1 digit or just a couple digits will drastically change your overall heating load for that building and the infiltration. So it is very, very key that the right details are gained in the exact building details, because I have seen selections go from 4 units to 8 units to 10 units, all depending on a very small variation of the actual insulation value of the roof and the walls. So it is very key that that is exact of what the building actually will have. Heat distribution. So how to distribute the heat in the warehouse. Do you use ductwork, push it around the space, have it in evenly distributed? Do you just move a massive amount of air? Just highly, highly pressurize, hope that works, prevent any infiltration. HVLS fans, what are they? You are turning over the air, so you're cycling it from the top to the bottom, dissipating that high heat bubble potential up in the ceiling to very well even the air temperature across the space, which would then require less heating because you're not wasting it, getting it captured up in the ceiling. And below there, so that is an example of a Greenheck direct gas space heating unit, or Greenheat line. So that has our direct gas burner that has a variable air damper below it of the burner itself to keep pressure, as well as the mixed flow fan. So it's a Greenheck mixed flow fan mounted in there, and then with a Greenheck diffuser, which we also, all of that is made in our facility. High velocity discharge, so throws the heat, induces the airflow. So what we're talking about there, that diffuser is specific in a lot of applications. You'll see the 45 with the elbow and then blasting down towards the floor. And we're going to get into kind of how that is set up in the warehouse and where you would place those units to get the best value out of it. So high velocity discharge example. Looking at the fluid dynamics here, you can see this is again what I just had said, that 45-degree elbow, three-way diffuser, blasting down into the space and across the floor. So if you're looking where it says diffuser there, that would potentially be the wall if you had a lot of dock doors, and we are going to get into that more. But what it's showing is you're moving the air down across the floor, trying to get the greatest throw, and then eventually it will come back up. Now you can see it. This is a much larger of the same picture. It's zooming out. You can see once it finally does that throw, kind of drops off the wind speed or the air speed, it is going to create a full turnover in the space. So it will help to kind of diffuse that high temperature up in the ceiling, not using a fan. So obviously the larger the space, the more difficult it is for that air and that heat to travel around. So that's when you do need to start applying more and more other options, more units or more HVLS fans, things like that. Obviously a much smaller space, if you only have one unit, can do a really great job of doing this exact kind of diagram of how it turns that air over. So creating that rotation. So typical warehouse layout, what you're looking at here is, so you have the dock positions on each long side of the building. So where would you put the units? So you have pallet racking on the inside, the heat load concentrated near dock doors. So you're going to want to have the units on the walls with the most doors. So in this case, most likely they would have units spread on each side, the long sides of that building. That way you have the 45-degree elbows with a three-way diffuser, not blasting straight down and not blasting directly at the doors themselves, but actually down and away. If you go back here looking at that, again, that dock door would be where it says diffuser, and then you're blasting at a 45 down and away. So in this potential, you're pressurizing the center of that space, getting that turnover, and then creating that air curtain, that pressurization to block that cold infiltration of all those dock doors, keeping that space comfort, and especially not losing a lot of that heat because you don't have as much loss from cold air infiltration. So here's a drawing layout showing these 6 makeup air units in this type of application. Again, many doors along sides of the buildings. The units are mounted closest above the doors themselves, blasting into the center, pressurizing the space, creating that curtain. This is an example of a long building with 4 makeup area units where only one side would have the dock doors. Again, those units are mounted on the dock door side, blasting away, which would then hit the opposing wall, turn over in the space, and then push out through those doors. It's the same concept if you've ever walked in convenience store, Walmart, things like that, where you feel those heaters just blast on the fans right when you walk in and the door opens. It's creating an air curtain of heat to not let that cold air infiltrate into the building as you walk in. Key space heating design takeaways. So again, what do we just kind of talk about? Quick synopsis. Accurate skin loads critical to providing the most cost-effective system. Calculation is only as accurate as the information provided. Again, we're talking about the design, the amount of usable heat you need, the design skin load, the building losses. Introducing your pressurization mitigates infiltration. So again, when you pressurize a space rather than just an air turnover unit or circulating unit where you're just bringing it around, that cold air will hard penetrate and cause a much greater need for heat because you're not blocking the cold. Stratification increases the heat loss and operating cost. Main thing there, that hot air bubble moving to the ceiling, 85 degrees in the ceiling, 65 in the space, but still you keep applying more heat. Well, if you have those HVLS fans, larger space, you can turn that over, requiring much less heat because those room sensors aren't going to be sensing a cold temp down at the bottom of the building, whereas the top would be overheated. Take into account ventilation when selecting equipment. So the kind of a general rule of thumb there, CFM per square foot. You can use as a calculation method, obviously some codes or different areas around the country, as we know, vastly different codes, things like that to go by. But that's kind of a general rule of thumb going. A lot of people ask us, hey, when do I need to include pressure relief dampers, or when should I do this? Use an exhaust fan. It all depends on the type of building, how many doors. As you know, if you have 200 dock doors, there is going to be a lot of pressure loss there. You may not need as many, if any, pressure relief systems or things like that. So it all depends on application. Space heating equipment. So what do we see? Well, right here, direct fired comparison. Upper left-hand corner, you have our direct gas burner that is stainless steel construction with aluminum gas train. To the right of that is an IGX, or an indirect gas heater. So it's a furnace that we build and then put inside of a makeup air unit. Below that furnace, that is actually a DOES unit, so a dedicated outdoor air system. So that's looking at more comfort cooling, office spaces, things like that. We are seeing them pop up in a lot more markets now. I have not seen them in any warehouse application because you're not really needing that dehumidification, heat pump technology, perfect comfort cooling. With a warehouse, hey, I just don't want it to freeze. That's my main concern. Keep it at 50, those types of things. And then the bottom left-hand corner again, direct gas unit. That would be the older style with that forward curve fan. Whereas if you did not know, Greenheck no longer uses forward curve fans below 25,000 CFM. We are only direct drive plenum fans now for almost all those applications. That's again under 25,000 CFM. Above that, we still do use forward curve fans. So direct gas-fired heating comparison, or sorry, gas-fired heating comparison. You have direct gas versus indirect. Direct gas, you are what? You are heating directly in the airstream, open flame, going into the space in the air. You don't need any venting. Indirect, it is a furnace type, so you must vent those combustion fumes outside via exhaust. If the unit is mounted outside, downblast into the space, then it can just vent directly at the unit. Efficiencies, direct gas, you're looking at 92% efficient. With indirect, it moved from 80, it is now 81%. That is a new code moving forward. The reason that is 81%, especially for Greenheck, it does not require any condensate. So you don't have a pan, you don't run pipes, you don't run drains, all those extra things that you would need for installation. We purposefully keep it at that 81% efficiency to not condensate on the furnace. So it is a much better installation. Requires outside air, requires no outside air. So when you're looking at that direct gas, obviously we can never heat the same air twice. So you're never burning that same air in recirc. You can only heat with direct gas, fresh outside air. So we'll get into later, how do you actually perform recirc with direct gas? But looking at indirect, no outside air required. You can do 100% recirculation with indirect, again, because you're venting combustion fumes outside. Turn down, so we're talking about heating turn down capability. So 25-1 is the standard for direct gas. Now that is across the entire industry, not only us. You will hear 30-1 in some instances. If that is, they're only talking about the burner. The burner itself is 30-1. A direct gas unit as a whole is 25-1. That again, industry standard. And then turn down for indirect. Typical terminal strip unit would be 4-1. You do have the capability with a microprocessor or digital control to get up to 16-1. Not only that, but if you add multiple furnaces, you can multiply your turn down. So say you had 3 furnaces, which is the maximum on an IGX, which is 1200 MBH. Each furnace is 400 MBH. You'd be looking at a 48-1 turn down. So it's a pretty high turn down. But again, you now have a 1200 MBH system. So you're starting much higher to turn down more. And this is just talking about heating capacity. Really, the comparison of how direct gas equipment is much less expensive than indirect. So as you get larger and larger and larger, it is much easier to keep adding burners to direct gas versus adding full furnaces onto an indirect. So the cost will get exponentially higher on indirect where it would not on direct. Space heating type systems that you can see, other areas or other manufacturers may use infrared tube, air turnover, unit heater. What are those systems doing? Most cases, obviously with infrared tube or unit heaters, they're not bringing fresh air in. You're just tempering the space air, maybe slightly recirculating it with that unit heater, a fan, infrared tube. It's just radiating, getting that heat out, bouncing off the floor, creating that warm space. The issue there, infiltration. That's the big, big takeaway with warehouses. You're not blocking or pressurizing that infiltration. It's costing you much, much more in heating load to try to keep that space temperature. Below that, you have the 80-20 recirc. So that is the first talk here about how you perform recirc with direct gas. We're looking at that, the blue arrows there from the left to the right, you see them come in. There's a 20% and an 80% damper. Anytime that unit is operating, that 20% damper is open so that air flows with a divider in the middle across and through the burner. While at the same time, if you are in full recirc, the larger damper would be closed to the outside. The larger damper is then open to the bottom, bringing in that 80% of the air as recirc. It mixes after the burner. So that's the big takeaway. You are never heating the same air twice. You never are building up any levels of combustion, fumes, CO, things like that. It's highly regulated. You cannot do it. So that is why it mixes after to ensure that is a very safe and applicable unit. And then the high temp, 100% outdoor air. What is that referencing? Well, with 80-20 units, you have a maximum of 110-degree discharge temp. With high temp 100% outdoor air, or our space heating units, our green heat, that is 140-degree discharge temp for those units. Space heating system comparison here. So looking at efficiency, capability, and destratification. So again, infrared tube, unit heaters, that lower efficiency. A unit heater itself can slightly get higher, but the key detail there, no fresh air. You are not bringing in, you're not pressurizing, you're not blocking infiltration. And then also, where's that heat going to go, especially if you're not moving so much air? It's going to rise and create that bubble up top where you're putting more and more heat and getting a very hot ceiling. Then looking at 80-20 into that whole 100% outdoor air, that's when you're providing the outside air, pressurizing, blocking infiltration, getting turnover, trying to help with that destratification. So those are the key details there, why using makeup air for space heating is really the best option. So 80-20 recirc, this is more in detail there, a larger picture. Again, I described that already, showing that 20%, 80% mix. Going through, there's a plate in the middle blocking air mixes after burner and then gets into the space. So continuous during occupancy, direct gas fired, the efficiency is 92%. Outdoor air is variable 20 to 100. Again, anytime the unit is on, that little damper on top, 20% is always open, and then you can fluctuate whether you're in recirc or not. High velocity discharge, high air volume, limit stratification. So with those units, where do you see them mostly? A lot of warehouses, I would say 75% of the time are 100% outdoor air units. When are you going to see this? Possibly a smaller application is when you'd see a recirc unit. Why? They would put a building pressure sensor and have their recirc dampers modulate to the building pressure sensor. So say all the dock doors are shut, service doors are shut, maybe it's in unoccupied mode, something like that. The unit would then fluctuate to have 80% recirc. So you're bringing in, you have a lot warmer air because you're recircing a lot more from the space. That means your heating load is going to significantly go down. You're going to burn less gas. You still have some pressurization to help block infiltration, but you don't need as much. You're not cranking a large amount of CFM into the space. That recirc then can modulate on its own with building pressure. So I see that a lot with smaller garages, smaller warehouses, municipalities, things like that, service stations. A lot of times you see the 80-20. So 100% outdoor air units, typical cycle on a call for heat, but can run continuous for ventilation. So what you have is a summer winter mode, where winter mode would be the unit will only come on in a call for heat. So you have a thermostat in the space, thermostat trips, the temperature drops below, there's 50 or 55 degree set point. Unit comes on full bore, 140 degrees, 100% outdoor air CFM, pressurizes the space, brings that space up to temp, kicks off, and then we'll cycle on as such. So it's 100% outdoor air, again, 92% efficient. High velocity discharge distributes the heat and limits stratification. So when you do get that full outdoor air burst pressurizing, you also help to defeat that stratification. So what kind of controls do these units come with? Two real options here. So one, your older style terminal strip. So this is an actual picture of inside the control panel of a unit, just identifying some equipment there from left to right. So you have your outside air T-stat. So it's your inlet air sensor. That's a lockout. So you set it to say 60 degrees, the unit will cut out heat 60 or greater, and it will just continue bringing in fresh air. Heating temperature control, that is your amplifier. So that is controlling the modulation of the modulating valve in the gas train. The HLC1, it's not highlighted, but that's going to be your high limit cutout. So normally from the factory, it's set to 160. So it's in case the unit starts overheating, it would then trip out, requiring a manual reset at the unit. To the right, terminal strip interface we use in all of our units, whether it be terminal strip as defined or microprocessor. All of our connections are done by a black Wago block. That is what you are looking at. You can see in detail, since it's kind of zoomed in, there is a small hole in between each block of terminals. There's 2 and 2 left to right that are all connected together. That is for actually plugging in your multimeter. You can lock it into the common, and then say you're trying to diagnose an issue with the gas train or why the unit may not be firing. You can plug right along from terminals that are normally listed 102, 103, 4, 5, 6 as you go up, and you can just sit there and probe power, power, power. And then if you don't have power, you now look at the wiring diagram. What was between the two? Now you know. So you can easily diagnose, maintain, perform startup. It's a much, much user-friendly unit, especially for technicians. We want people to be able to use the units very easily, understand them, and feel very comfortable working on them. Happy technician means a good startup and a good rapport, especially when they're working on your equipment. And then on the right side there, remote panel. So that would be the option you can select when you're talking about space heating, is it's going to have a room temp sensor. So it'll have a room temp sensor in that panel. We have two options: in industrial, which is painted, and then a severe duty, which you can see in that picture. That is a stainless washdown rated NEMA 4X, NEMA 12 panel for those like wastewater treatment or other applications where you may need it. Now looking at the control options for microprocessor. So that's the other side of the house. This is the future, what all units are going to. Most units are now microprocessor. So what are you getting with that? You're getting a digital control. So we just released a new controls platform about a year ago. It's called our Gen 2 controls. It's a much smaller microprocessor, as you see in the center of the screen there. We've changed all the viewing screens, we've changed the menus, everything in it. We've tried to make it more user-friendly. We've taken advice from technicians, people in the field, our reps, and we really use all that information to build the best product. So what does it use? You can tie in remote displays, so you're going to have a reflection of that screen in a remote location with that remote display that would plug into the unit. You can use BMS, so you can use BACnet, MSTP, IP, or Modbus to connect up to that. You can read or write all the available points inside that, as well as obviously operate it at the unit. What is it going to use? It's going to use a Corel device for a room thermostat, so that can be adjustable in the space. So warehouse application, you'd see that down in the space, can adjust it up and down. And then also, say you're using building pressure to modulate either maybe fan speed or the 80/20 recirc, things like that. You can use pressure sensors, a lot of Mammoth brand sensors in there, and then also CO2, a lot of safeties, smoke, fire, different things like that can all be tied into that microprocessor. It's a very user-friendly. The main screen on it, what you see right there in the center, that's a big takeaway. Moving on here, you see the screen upper right-hand corner there, active alarms, where it says that. That's going to be your home screen now. So the way we laid out our microprocessor platform is we want people to be able to see what's going on in the unit without having to hit any buttons. So before you had a main menu, you go to set points, you scroll through all your items, no longer. Now you walk up, that's what you would see. It's a default screen after you're done actually accessing the micro. You'd see what's the unit supplying, what's the air coming into the unit, what is your set point, and what is it doing. Fan symbol means the fan is on, flame symbol means it's heating, a turning snowflake would mean it's in cooling. That would obviously not be a warehouse application, but just in general. So with the microprocessor, you have standalone with optional BACnet. So what does that mean? That means the unit can operate everything itself. All the set points can be done, schedules made. You don't have to connect to it, but you do have the options there of connecting into BACnet. So settings can be default to local or obviously BACnet, looking through that, and you have the different capabilities. It no longer uses a card, so there's no BACnet cards. Say a unit is ordered in error, hey, I need BMS later. We can just download the program on, get the access code onto it, and then you're up and running. You're not waiting for shipping of cards or different devices. User-friendly navigation, we've changed all the screens around to be a much better use and easier to find different set points or different controls in the unit. Pre-programmed and flexible. Say you have a customer with many, many warehouses. They want to maybe have a custom home screen. They want to have their company name. They maybe have a special sequence. We're always willing to work with people and different types of specials to really get what they want, meet a special program or sequence that maybe other manufacturers cannot. So all options loaded into the controller can be modified in the field. That's a big takeaway. You can call our tech support. They'll walk you through changing many, many options. If it wasn't ordered incorrectly, most likely we can change those details without the need of shipping any devices or other things in the field. So it makes it much better, less downtime. What is this? Microprocessor Web UI. It is a new connection that uses Cat5 cable, so internet-based cable there. You plug right into the microprocessor, and then you can plug into either a network device of the building, your laptop, a tablet, and then what do? You don't actually need to be on the internet. You don't need to download a program. You don't need to get any special codes. You go into a microprocessor of the unit, you pull up the IP address, and then you type that IP address in any general web browser on whatever device, tablet, laptop, or network you're using. It would then pull up this exact screen. It's a full layout of the unit. Obviously, that screen shows what would be more of a DOAS unit with an energy wheel, but it's just because it's showing all options available, and then it would highlight what you have. But you can go through, change set points visually. It's a much easier way to see. You can check alarms, settings, data logging, all those options are available. Say you had 6 units on a warehouse, the warehouse had a network, they plug them all in. Someone could go on site as long as you are on the network. So that's the key security detail there. You have to be tied into that network via VPN or directly on site. You can then draw the units onto your computer through their IP address and view change adjustments or check alarms on all of them. So it's a great way a technician could come to a warehouse, check all the units if they had the IP addresses, and be able to leave without actually having to go up to every single microprocessor and check them. Many warehouses now are using these type of applications. I've been working with quite a few customers that really like it. They have a lot of network tie-in, and they could actually VPN to multiple buildings, and a single person in an office can check 10 warehouses and 100 units in an hour or two without ever leaving their office. So it's a pretty amazing technology. So the other detail there is service features. With the new microprocessor, alarm and data logging, instead of 99 alarms, you're checking 999. So it's logging many, many more alarms. Not only that, it's not going to just say, hey, alarm, fan enable dropped or something like that at a time. It's going to give you more statuses. What was happening? What was the unit trying to do? Was it trying to heat, cool? Was it running just fresh side air? What was the set point of the damper? Different things like that. It's going to provide a lot of information during each alarm, so you know what was actually happening at the time. Service overrides, a technician or someone working on a unit or trying to perform a startup can force things into operation. They can force heating, force cooling, change damper position without having to actually change variables, where in the past you had to say the unit was set up for BMS fan control or heat. You'd have to change that all to local and then change it all back after you were trying to work on it. Now you can just go into service override screen and force everything over to try to work on it or perform testing. Integrated direct gas and indirect commissioning. So this is the big one. This is brand new for us. It's been around for about 3 years with indirect. So furnace commissioning, you'd go through step by step, tells you what to do, how to do it to set up a indirect furnace. That's on every furnace controller itself. But direct gas hasn't been around. We are the first manufacturer to introduce direct gas commissioning. So you go to a commissioning menu, it takes 2 clicks in that micro to get there. After that, you go through step by step. As you can see on the screen, it says in depth. Starting off, the number one thing, what's the largest issue that you could see on a direct gas unit is pressure differential. People are not checking it or adjusting it. They start up a unit with electricity, they say, hey, I saw the fan spinning, and walk away. They're not performing a proper startup. With this, it takes you along every step of the startup, and as long as it's followed and you have to click next to each screen, once you're completed, the unit is fully started up. No detail was missed. Not only that, but if you reference those two in the third and fourth screen, it says target and actual for pressure drop. You're inputting data. So it gives you a range and an input. If you input something out of the range, it will then take you out of that, give you a screen stating what IOM number to reference and the page of how to do it. So it's going to tell you what to change if you're not getting the correct data. Not only that, if you put in a value that's within the spec and you go to the next page, it saved it. Once you're done with the startup, you have a saved startup report with the date and time on that microprocessor. Anybody can come up, plug in, download a PDF startup report. Now it's always going to be saved. So it's not a handwritten startup report. It's lost to the wind. No one knows where it was. Hey, yeah, I just know it was started up at some point. Well, now you can go up and actually check at the unit. And all of these functions I just talked about, the integrated commissioning, the service features, the logging, web UI, the connectivity, those are all standard with every microprocessor from Greenheck makeup air units. So all those functions are part of our new generation 2 controls. So applying direct gas fired equipment. So when you're applying it to an actual system here, remember, large buildings have significant ventilation load depending on the compliance. Depends on what's happening. Obviously, a large building with manufacturing, grinding, welding, dust, things, you're going to have a much, much higher need of turnover and ventilation load, where a general warehouse with electric forklifts is not going to have much of a turnover requirement, if any. It just has a heating requirement. Direct fired equipment, best situated for ventilation. Why? Because that cycle of 100% outdoor air, it comes on, it heats, it turns off. It blocks that infiltration, but then you get that quick turnover. You're not running a unit continuously that might be half recirc, half outdoor air. It is a very efficient unit, 92%. And the initial up cost, direct gas unit is one of the least expensive units out there, but provides the best heat. So addressing the skin load and separate space heating equipment. So what's that talking about? It's the overall infiltration, people, or loss through poor insulation or walls. Do you add additional heating in those spaces where it's very cold, or say you're in a corner with many doors, it always gets cold in that corner. What are we going to do? Hey, we'll add an air turnover unit, add a space heater, or you can increase the supply air, better turn over the space, better pressurize. So that's the key detail there. So what is this talking about? So if you're discharging 65-degree air, it's going to be running a lot longer to keep that space hot. Say you make a building extension, you add on more, but you need more heat. A lot of indirect units or space heat units, you need to add more units. With direct gas, you can add more burners. So really, that's the big thing with direct gas units. If there's enough space inside, you can ramp up the heating in that unit. You can just keep adding more burners, such as this case. Each burner is 400 MBH. So this at 527, it would have had two burners or 800 capacity. They ramped up to 1134 MBH. They just added one more burner. It now is a 1200 MBH capacity, which brings that temp up to that 140 discharge temp. So now you have 607 usable MBH with minimal cost increase because it is just a burner add. Examples, discharge temperature with its sized warehouse, 2427 MBH skin load, design temp, design space temp, and CFM required. So looking at this, I want to keep the space at 65 degrees. But what's my discharge temp? Is it going to be 65 even? Well, that's just going to be running all the time, nonstop. It's never going to actually reach that number. If you're discharging 90, 89,000 CFM required. But as you go up to that 140, it cuts it way down. Less CFM required. Why? You're discharging a much hotter temperature. If anybody has any questions about the 140 versus 160 at the end, we can get into those details. Ventilation requirement. So that's that rule of thumb is at 0.06 CFM per square foot that we were talking about earlier. 80-20 recirculating units. So restriction of air temperature is rise based on the amount of outside air. So looking at that max equivalent temp rise outside air. So the higher percentage, the max equivalent temp rise that would be needed with that. So obviously more outside air, the more you have to raise the temp up because return air is going to be warmer because it's from in the space. So the majority of the industry has settled that 20% minimum outside air allows 90-degree discharge temperatures in most applications. So another kind of general rule of thumb there. 80-20 recirculating units, the airflow. So example again, same warehouse there, same skin load, looking at 90-degree discharge temp. Why? Because that 90 or the 100 is the maximum you can do with a recirc unit. You can't get those high discharge temps. Why? Again, think about it. 20% outdoor air. That's only passing over the burner. So you have to superheat that air because once it mixes, you get the heating loss. So there's no good way of trying to get those 140 degrees or higher temperatures because you would have to heat that 20% of the air so hot to then mix and get the 140. It's just not possible. It would be overheating the burner, overheating that top of the control cabinet, trying to mix it in. That's why you have a overall, the max discharge temp on a recirc or an 80-20 unit is going to be either 100 or 110, where 100% outdoor air is the 140. That's the reason, and that's the difference there. So what does that mean? It requires more CFM because you're recircing more, less outdoor air, less heat load. comparing direct gas-fired equipment. So 100% outdoor air advantages, minimal air volume, lower first cost. Research units, variable outside air. So again, I had mentioned that say they have a building pressure sensor, everything's off, unoccupied, they maybe want that to fluctuate to more return. That's a good application. Higher air volume for heat. You're going to have to run that 80-20 a lot longer to get the space up to temp because of that discharge temp. Disadvantages for 100% outdoor air, possibly for over ventilation. Yes, if every single one of your units, and you have many units, is 100% outdoor air, and they're all blasting into the space, you're going to have a large positive pressure. You're going to need some building pressure relief if a lot of doors are closed. The disadvantages for 80-20, higher first cost, the unit in general is more expensive, and higher operating horsepower. Why? You need to move a lot more air because you're recircling. Ventilation requirements, 100% outdoor air units typically cycle on a call for heat. Run times are about 30% over the entire heating season. Ventilation rates depend on local codes. So we had talked about that before, but the ASHRAE 62.1 requires that 0.06 CFM per square feet. Size, 100% outside air units for heating requirements and verify airflow rate meets ventilation requirements. And if you're sizing 80-20 units to meet ventilation rate at minimum outside air, that's the key detail there between the two, is that 100% outdoor air bringing in much, much more CFM. You never have to worry about hitting an air turnover, where with an 80-20, you may have to look at, am I meeting that air turnover? Night setback style controls allow units to cycle during unoccupied times. So we have different control options, especially with a microprocessor, where we can sense the room temp and have units come on maybe at a lower CFM rate or more recirc, things like that, to just ensure that space may not freeze in an emergency. Draw through blow through. What are we talking about here? This is a big Greenheck versus other manufacturers. On the top is Greenheck. We do a draw through design with direct gas. Below that is almost all other manufacturers are doing a blow through. Our design is creating an even flow, even pressure, unturbulated air. You're bringing in what we would call clean or non-turbulated air across the burner. Why? When you're doing a blow through, you are pushing air over that burner. It's uneven, it's whipping, it's mixed. You may have pressure fluctuate. That can cause a unit to not work properly. It's definitely not going to be as reliable as a draw through design. So a lot of times a spec where it's a Greenheck unit versus others, you'll see a weird CFM. You'll have the same MBH, a unit for a unit. Anytime you spec something, especially for space heat, what we try to say, only look at heat. Heat load is the only thing that matters. So say a spec says 867 MBH, that's what you care about. Make sure no matter what the selection is, it's 867 MBH. But what if the CFM is different? They're going to see that. They're going to say it. A Greenheck unit will say, in this situation, 6522, 6522 CFM. The competitor would say 5000 CFM. Well, what the heck? Why can they do less CFM? What's their requirement here? They're measuring the intake air at the fan. That air is cooler. Cooler air, you're moving less of it. Because your air is then heated, it's expanded, you're moving more CFM. So a lot of the times, this is our number one question with warehouses and space heating. Where's the discrepancy with CFM? Why is it happening? Because we are a draw through design, they are a blow through. We are both measuring at our fan, but they're measuring at that cold air where we're measuring at that expanded hot air. So that is why you have a CFM difference. And we say focus on MBH. And that's just what I said. All right, so Greenheck as a whole, looking at our space heat units here, this is going to be our last slide. We have a lot of flexibility with our equipment. We can apply to numerous applications. You can work with our pre-sale team, which is myself and others. We can do special design requests. We help many reps every single day looking at specifications, trying to figure out those real difficult details a lot of the times with really interesting specs, how we can meet them. Our lead times, especially right now, you're looking at a 4-week lead time across the board with all makeup air units at Greenheck. Other than a PDX, which is a package cool unit, that would be a 5-week lead time. That is the current lead time. It goes week by week. We refresh it, but that is what we are currently standing. Experience you can trust. We're definitely not new to this market, over 40 years of experience doing this. So our patents with that draw through design and also our barometric or our gravity damper below our direct gas burner for variable volume, we are one of the only manufacturers performing those specific details because we were the first to do it and the first to patent it a long time ago. We stress that service after the sale is just as important as before. Our tech support team does an amazing job. They're there 5 days a week, 7 to 5. We'll have our tech support. They'll be sitting on the phone for 3 hours with a gentleman or a lady on the phone doing diagnostic work, helping them out. Sometimes we do site visits. We always try to help people best we can. We want to make sure they know Greenheck will provide the best service and be the easiest to do business with. And lastly, innovation. We have many unique things we do here at Greenheck when it comes to makeup air, emphasizing our patented bypass damper and variable volume, which I said, and the high turn down furnace, direct drive options, mixed flow plenum fans, and our controls. The key detail here, every single one of our makeup air units under 25,000 CFM, as I said, they're direct drive plenum. What does that mean? VFD. So every unit has a VFD in it. Moving forward, the industry is going to be all microprocessor. We have that option, and we're providing that option at a much lower cost than almost anyone else. We have brand new designs, sequences, and also customization we can do with warehouses and space heating and looking at different variations. But the key detail is many people out there are still doing forward curve fans in front of the burner while we are doing direct drive, draw through, very efficient and long lasting units. That's the key details there. So that's all I have. Open it up to questions. Who would have the first question?